All right, hello everybody. Today we are going over Unit 1, Lesson 4, which is on composition of mixtures in the AP Chemistry curriculum. Today's learning objective is to explain the quantitative relationship between the elemental composition by mass and composition of substances in a mixture. We're learning the difference between pure substances and mixtures. Pure substances are made of just one type of particle, while mixtures have two or more kinds blended together in different varying amounts. We'll also look at how scientists use elemental analysis to figure out what's inside a substance and check how pure it is. Before we go into mixtures, let's talk about what pure substances are. Pure substances come in two forms, elements and compounds. Elements are made up of just one type of atom. So for example, if you had a sample of gold, in that sample of gold, all you have is gold atoms. If you're looking at a sample of oxygen gas, the only thing in there is oxygen atoms. Then when we talk about compounds, compounds are made when two or more different atoms are chemically bonded together in fixed ratios. For example, when we have water, for every two hydrogens, there is one oxygen. And for example, table salt, we always have one sodium for every one chlorine. So it's fixed ratios of chemically combined atoms. The key difference here is that elements are the actual building blocks and compounds are those blocks combined in set ways. Unlike a pure compound or an element, a mixture is going to have varying composition and is made up of several pure substances. And I wanted to show you this diagram on the bottom here because AP Chemistry loves to throw in particle diagrams. So down here, there is a clear difference between a mixture and a compound because in the mixture, we have two different types of pure substances. We have O2 molecules and we have H2 molecules. So that gaseous mixture is a combination of two pure substances. And then on the right, we have a compound or H2O molecules that is a pure substance because it is just one type of molecule and each molecule is composed of the same composition of two hydrogens per one oxygen. So this diagram shows us how matter can be classified in terms of pure substances versus mixtures. So under our pure substances, these can either be elements or compounds, which we already talked about. And then on the other side, we had mixtures. Mixtures can either be homogeneous, meaning they have the same composition, or heterogeneous, which means there are different visible parts of that mixture. And then if you ever are talking about a solution, just know that that is designated under the homogeneous category because it's uniform composition throughout. So when we talk about homogeneous mixtures, we know that they have a uniform composition throughout, just like shown in that diagram on the left there. However, just remember that composition and properties can vary from one sample to another. So for example, if you have a mixture of salt water and you make several samples of salt water, even though they're all homogeneous, you might have a higher saturation level of salt in one than you would the other. So it's a different composition and properties in each one of those samples. And then different components can't be seen with the naked eye. So for example, salt water, if you're looking at a glass of salt water, you can't necessarily tell that there's salt in the water unless there's some sort of buildup on the bottom. But that would be a homogeneous mixture if you could not see any salt particles in there and just looks like water throughout. So other homogeneous mixture examples could be a mixture of air, of vinegar, which would be acetic acid and water, brass, which is copper and zinc. You can't see the copper, you can't see the zinc. It just looks like a new type of metal, which is brass. And then we go over to our heterogeneous mixtures. So these are separate, distinct regions within the sample that have composition and properties that vary from one part of the mixture to another. So these different components can be seen with the naked eye. A very common example would be like a chocolate chip cookie. If you're looking at that cookie, there are different compositions in that cookie depending on where you're looking. Other heterogeneous mixtures would be sand and water, or a salad with different components, trail mix, oil and water. These things you can see two or more different aspects of that mixture with your eyes. All right, so let's look at some more particle diagrams. So the first question says, which of the following samples are considered pure substances? So I want you to pause the video and see if you can answer that question. So if it's asking you to identify a pure substance, you're looking for either an element or a compound. So if we look at A as an option, you can see that there are what look like water molecules. It could be a different type of compound, but it looks like water molecules. Since they are all the same molecule and that's all we have in there, that would be considered a pure substance. So A is one of the answers. And then let's go down to C. On C, we can see that there are molecules, but there are two different types of molecules. So that would not be considered a pure substance. That would be considered a mixture. And then going over to B, we have molecules, but they are of the same atom. So I'm going to guess that these are, let's say, oxygen atoms. In this sample, all it is oxygen. So that would be a pure substance. So B would be the other answer for pure substances. And then finally with D, we have another diatomic gas molecule, it looks like, with the red, and then we have another molecule that has 2 parts of one atom to 1 part of another atom. So those are 2 pure substances combined together, so that would be also a mixture just like C. The elemental composition of a mixture can be used to determine the relative amounts of the pure substances that compose it. So when we're talking about elemental analysis, what we're doing is finding the relative mass of one or more of the elements in the mixture, and then we can use stoichiometry and the other information we're given to actually solve for the analysis of that element. And when you're trying to find the percent mass of a compound within a mixture, it's the same formula that we used in the last lesson when we talked about the part over the whole times 100. It's just that the whole looks different here. Instead of an element over a compound, now we're doing a compound over the whole mixture. So it's the same concept, just with different words plugged into the formula. So let's start with an example. A 2.4 gram sample of a mixture of calcium chloride and sodium chloride is found to contain 0.12 grams of sodium. What percent of this sample is NaCl? So I'm going to start off with, what is this question asking me? It's asking me for the percent of NaCl in the mixture. So percent of NaCl. I know if I want to solve for percent NaCl in the mixture, I need the mass of NaCl over the mass of the entire mixture. And then I would multiply that by 100. Now, I already have the mass of the mixture because it already gave it to me. So I already know the bottom, or the denominator of this equation, is 2.4 grams. Now, what I'm solving for here is the numerator, or the grams of NaCl, and I can get that by using stoichiometry. So what I'm given is 0.12 grams of sodium, and I need to get 2 grams of NaCl. So I'm just going to do basic stoichiometry. I know in 1 mole of sodium, I have 22.99 grams of sodium. I know in 1 mole of sodium in sodium chloride, it's a 1-to-1 ratio. So for every 1 mole of NaCl, I have 1 mole of Na. And then I want to end up with grams of NaCl, so I have to take this one step further. And I know in 1 mole of NaCl, I have the molar mass of NaCl, which is both of the molar masses combined. So that would give us 58.44 grams. And before you do all this math, I do recommend that you make sure your units have canceled out. So grams of sodium are gone, moles of sodium are gone, moles of sodium chloride are gone, and I'm left with grams of sodium chloride. And I can go ahead and solve. So I get 0.305 grams of sodium chloride. And now I can go ahead and put that into my final equation that I'm using. So out of the mixture, 0.305 of the grams is sodium chloride. So if I divide that by the mass of the entire mixture, that will give me the percent of sodium chloride. And for my answer, I get 0.127 times 100, which would give me 12.7% NaCl. However, 2.4 and 0.12 are both 2 sig figs, so that would actually round up to 13% NaCl. All right, next example, a 5-gram sample of a mixture of calcium carbonate and silicon dioxide contains 1.5 grams of calcium. What percent of calcium carbonate is in the mixture? So since this one is kind of similar to our last one, I would like you to pause the video and try this one on your own. All right, so let's go over it. So we are trying to find the percent of calcium carbonate in the mixture. So in my numerator, I have my grams of calcium carbonate. In the denominator, I have my grams of mixture, which is going to be 5 grams. So I'm solving for grams of calcium carbonate, and I am given 1.5 grams of calcium. So I start with that, 1.5 grams of calcium. Then I'm going to convert that into moles of calcium. Then I'm going to convert from moles of calcium to moles of calcium carbonate. And I know in 1 mole of calcium carbonate, there is only 1 calcium. And then in my final fraction, I do need mass of calcium carbonate. So now I'm going to convert this into grams. And then you can go ahead and just make sure all of your units cancel out. Grams of calcium are gone. Moles of calcium are gone, moles of calcium carbonate are gone. I'm left with grams of calcium carbonate. And I get 3.746, so that's my grams of calcium carbonate. I'm going to divide that by 5 and multiply by 100. I end up getting 74.918, and I need to look at my sig figs. I have 2 sig figs and 2 sig figs. So my answer is going to round up to 75% calcium carbonate. All right, this next question is something that AP does like to throw on their multiple choice, and it's just reasoning. It's not really math, it's just understanding how to do the math. So it says a jar labeled NaCl contains a powder. The table above contains information determined by analyzing a sample of the powder in the laboratory. What information in the table is most helpful in determining whether the powder is pure NaCl? So we know from doing these example problems in the past couple slides that in order to solve for whether it's pure NaCl, we have to have some sort of information on the composition of the elements within that compound. So saying that it has a mass of 27.3 grams, that doesn't give us any information because anything can have a mass of 27.3 grams if you make it that way. Then looking at density, again, it doesn't give us the right information to actually solve if that is a certain percentage of sodium and a certain percentage of chlorine so that we know it's pure NaCl. And then finally, a lot of things can be the color white. It does not work in this specific scenario. So the answer here would be the mass percent of sodium, because with that information, we can go ahead and convert using stoichiometry to make sure that it is the correct composition in sodium chloride and match it up to see if it's pure. A student obtains a mixture of the chlorides of two unknown metals, X and Z. The percent by mass of X and the percent by mass of Z in the mixture is known. Which of the following additional information is most helpful in calculating the mole percent of XCl and of ZCl in the mixture? So the first thing I want you to kind of think about is any answer choice that has to do with chlorine. If you're given more information about chlorine, that is not very helpful because chlorine is in both of the substances. So A would not be a great option choice, and D would not be a great option because knowing more information about Cl doesn't help identify the mole percent of XCl and of ZCl because chlorine is in both. And the way that I kind of problem solve this question is if it's talking about percent by mass and I have to use something with mole percent, I should know that in order to convert and use stoichiometry, I'm using the molar mass to get from mass to moles or vice versa. So the clear option for me would be B, but also density would not help in those calculations. All right, this final question says each student in a class placed a 2-gram sample of a mixture of copper and aluminum in a beaker and placed the beaker in the fume hood. The students solely poured 15 milliliters of 15.8 molar nitric acid into their beakers. The reaction between the copper in the mixture and the nitric acid is represented by the equation above. The students observed that a brown gas was released from the beakers and that the solutions turned blue, indicating the formation of Cu2+ ions. The solutions were then diluted with distilled water to known volumes. The students determined that the reaction produced 0.01 moles of copper 2 nitrate. Based on the measurement, what was the percent of copper by mass in the original 2-gram sample of the mixture? So I know in this problem, I am solving for the percent of copper in the mixture. So I know I'm going to need my grams of copper, and I'm going to need the grams of mixture. Now, I already have the grams of mixture. It was given to me. It was a 2-gram sample. So I need to solve for grams of copper. Now, I'm given moles of copper 2 nitrate. So using that given information and the balanced chemical equation, I can go ahead and solve. So we're starting with 0.01 moles of copper 2 nitrate. I'm already in moles, so I can go ahead and look at my balanced chemical equation. It is a 1-to-1 ratio, so I know for every 1 mole of copper 2 nitrate, I have 1 mole of copper. And then finally, in my equation that I need to solve, I need grams of copper. So I know for every 1 mole of copper, I have 63.55 grams of copper. So let's go ahead and make sure our units cancel out. Moles of copper 2 nitrate, moles of copper, it's gone. We're going to be left with grams of copper. And then it's just 63.55 times 0.01, so that would be 0.6355. So we're going to divide that by 2 and multiply by 100. We end up getting 31.775% copper, but I need to double check sig figs. So when you are looking at sig figs in a question like this, please do not be distracted by all the other data points because you're only looking at the data points that you used for that math. So we used 2 grams and we used 0.01 moles. So this 2 grams is 3 sig figs because 0 after the decimal points count. And then this 0.010 is only 2 sig figs because leading zeros never count. So these zeros don't count in significant figures. So since our lowest number of sig figs is 2, our final answer needs to be 2 sig figs. So our final answer would be 32% copper. And that concludes our 1.4 lesson. If you have any questions, please feel free to reach out to me, and I hope you have a great day.